In today's third and final video, I have a practice problem that says to determine whether a mixture of 1-butanol and water will phase separate at 60 C in 1 atmosphere. And if so, what would the compositions be of the two phases? We're going to use the two-parameter Margules model, and we have given values for A12 and A21. So I've recopied the equations that we're going to need, the relevant equations. The first two equations are our phase equilibrium criteria equations for the two components. So let's just designate our component 1 is going to be 1-butanol, and our component 2 is going to be water. I also need to copy A12 and A21. Should pause the video while I do that. All right, so we've got our information imported into Excel. Again, these two equations are our phase equilibrium criteria equations, and these two equations are the two-parameter Margules expressions for the activity coefficients. Now, you notice that I have Excel open, and that is because I cannot solve this system of two equations, two unknowns by hand, because it is nonlinear. I can't isolate my unknowns x1 alpha and x1 beta. So therefore, my only option is to perform a goal seek or a solver approach in order to solve this system. Well, I could do it iteration by hand, but again, that's tedious, and I've used Excel all the way in this class up until now, so I'm not going to stop now. So two kind of different ways to solve this problem. I'll go through the first approach would be to solve it directly. So this is like the guess and check method. So I'm going to make a cell for x1 alpha and a cell for x1 beta. How do I want to array this? I'm going to go horizontally. X1 beta and X2 alpha. I usually don't do this. I usually don't explicitly write what X2 is, but here I'm going to. X2 beta, and I have gamma 1 alpha and a gamma 2 beta. No, gamma 1 beta, gamma 2 alpha, and gamma 2 beta. All right, I know why I'm arraying it like this, so that'll hopefully become clear later. My two unknowns here, as I said, are going to be x1 alpha and x1 beta. So I'm going to designate them as unknowns, right? So anytime I have an unknown that I want to solve in an iterative fashion, I'm going to need to make an initial guess. So let's just say that my initial guess is 0.5, 0.5. This is a horrible initial guess, by the way, which I'm going to talk about in a moment. X2 alpha is going to be 1 minus x1 alpha. X2 beta is 1 minus x1 beta. All right, so in the phases, I have a physical constraint that relates them. Gamma 1 alpha is going to be explained by this equation. So because I'm using alpha, I'm going to want to take the x2s from the alpha. So equals exponent of x2 alpha. All right, the equation for gamma 1 takes x2 first, square times alpha A12, so that's going to be $ plus 2 times A21 minus A12 times x1 alpha. And close out that parenthesis, close out the exponent. Okay, gamma 1 beta, I'm sorry, is the same equation but for the beta phase. So it's equal to exponent of x2 beta square times A12 plus 2 times open parenthesis A21 minus A12 times x1, which is in the beta phase. Now you notice that I $signed these, and even though I'm not doing a range of x1 alphas, I'm going to in a moment. That's kind of why I'm doing this. It's just good habit to get into when you're doing Excel. Anytime you have a formula bar like this and you're referencing a parameter, it's good to burn it into your brain that anytime you're referencing a parameter, something that will not change, you always want to $sign it. And I've got a parenthesis in the wrong spot, don't I? I need a parenthesis there. and that is going to make my parentheses, I need one more, right? Yep, one more, and that'll close out the exponent. Good. Gamma 2 alpha is going to be equal to exponent of x1 alpha squared times a21, and remembering my dollar signs, plus 2 times a12 minus a21 times x2 alpha. Close. Wait, do I should need to close 2 here, right? Oh, maybe not. Maybe not. Maybe I had too many parentheses. I have too many. Yeah, wait a minute. Nope, I made a mistake here. I need to have a parenthesis there. I need to open, close. Okay, that makes more sense. That's better. Gamma 2 beta is equal to exponent of, well, wait. Just double check. Gamma 2 alpha as x1 alpha. Okay, it's fine. Gamma 2 beta, all right, equals exponent of x1 beta square times a21 plus 2 times a12 minus a21 times x2 beta. All right, like that. Close, close. All right, I think I got all the gamma 2's correct. Wait a minute, I got the same equation. That doesn't look good. Oh, duh, it's the same because x1 alpha and x1 beta are the same. Maybe if I switch this up, if I try, yeah, something like that. Right, where gamma 1 alpha, gamma 1 beta are the same because my x1 alpha, x1 beta are the same. All right, everything is fine. I think I've got it correct. The next thing I need to do is set up my solver. So I'm going to have a constraint equation 1, constraint 1, and constraint 2. And these are going to be my 2 equations that I'm going to use solver in. So once again, when I use solver, I like to bring everything over to one side. So x1 alpha times gamma 1 alpha minus x1 beta times gamma 1 beta. That should be 0, and it is. Constraint 2 is x2 alpha times gamma 2 alpha minus x2 beta times gamma 2 beta. And these should both be 0, and they are. They're already 0. So what gives here? My next step would be to solver these to be equal to 0 by changing these constraints. So it already worked, right? I don't even have to solver it. You might think like, oh, I made an initial guess and it worked. Right, well, what's the problem here? The problem is that I guessed the same composition for the 2 phases, in which case you might say, well, is it really 2 phases at all? This is what we call the trivial solution, right? So I need some better initial guesses here. I'm going to need to guess something like 0.25 and, I don't know, 0.7, something like that. Something that makes the constraint not equal to 0. So now I might want to say data solver, and I want to set my objective cell, is my constraint 1 cell, to a value of 0 by changing variable cells that are my x1 compositions and adding the constraint that my constraint 2 is also equal to 0. And do not want to make unconstrained variables non-negative. I set solver up to go. And now what gives? Now I've got an initial guess that's right back where my initial guess was. And this is again another trivial solution, right? Because my compositions are the same, or roughly the same. So I'm gonna need better guesses here. So again, this is going to be the trivial solution. Anytime I'm close to the trivial solution, Excel is going to give me this trivial solution. So I'm going to have to be very careful about what I guess here. So let's make an initial guess that's something like this, 0.11, 0.62. And go to solver again and click solve. And now I've got something interesting. So this tells me that I indeed have another solution that works. So at an X1 alpha, that is 9% butanol and 90% water. I have phase equilibrium with another phase that is 64.5% butanol, 35.4% water. So this is kind of unsettling, and what I mean by that is I had to be pretty close to my initial guess in order to get solver to work. So maybe I might be trying for a while, or maybe I'm never quite sure if it keeps giving me back a trivial solution. Is that solution the only possible solution, or you know, is there a possible solution out there that I'm just not seeing? So another way that you could do this is you could make a graph, kind of similar to what I sketched out in the other Excel, in the other video on OneNote, where you could see kind of is the system stable or unstable, and it kind of gives you an idea for what your compositions are. So instead of solving for one variable, let's try and use the graphical approach. So let's plot as a function of x1, and let's start at 0, and we'll add by my usual 0.02 every time, and we'll do 50 data points. Not a problem for Excel to do that. And one more, okay? And I want to plot GE over RT. All right, so for the 2-parameter Margules, I had written this. Let me see if I can grab it. This was from an earlier video today. So del G mix over RT. And I want to plot this as a function of x1. All right, so I've got equals x1 times x2, 1 minus x1, times A21, and this is why, again, it's a good habit to dollar sign it, because here I am going to need to dollar sign it because I'm going to copy this formula all the way down. A21 times x1. Let me just make sure I didn't make a mistake with my parentheses. I did make a mistake with parentheses. I need to parenthesis there, and I need to plus A12 times 1 minus x1. Close, close. Okay, that looks good. Plus x1, oops, not equals, plus x1 times ln of x1 plus x2, 1 minus x1, times ln of x2, 1 minus x1. All right, I get a number error because I've got a 0 there. That's to be expected, but I copy that formula all the way down. Now let's go ahead and plot this delta G mix as a function of x. So insert a chart. This is a model, so I'm going to want to have a straight line there and change my x-axis to be like so. All right, so you can again use this plot in order to give you a better guess at what your answer should be. And it's not looking perfect. Let me double check. All right, I've double checked. I've got the right equation here. The thing that was tripping me up is that there is no maximum here, but that's actually not a requirement for the phase equilibrium. So if you look real closely at this curve, I got it. It's concave up in this region and also concave up in this region, but it's concave down in this region. And that indicates that there is an inflection point somewhere. And then that's all you need for an instability to occur. So it doesn't have to be very exaggerated like that. And I know that because I can draw a tangent line, or I can imagine a tangent line that connects these 2 points. So those 2 points where I have a tangent line that connects are going to be what I use as my first initial guess. So if you can eyeball it. I mean, it doesn't have to be super close. So maybe if I guess here 0.05 and 0.8, let's see if this gives me the correct answer. So this is a strategy that you would use to obtain your good first guess. So you would plot G mix over RT as a function of x1, And then wherever you've got this minimums, or a better way to visualize it would be if you drew a tangent line that connects 2 points underneath the curve, what would the 2 points be? And again, I'm looking at about 0.05 and well, it's got to be a little bit less. Let's say 0.75. Right, those 2 points I could connect on a tangent line. And let's click solver and see if it gives me that same. All right, it gives me the same solution here. So this is a solution to the problem. I would say that it does phase separate to answer the question, and the resulting compositions of the phases is that the alpha phase, the water-rich phase, will be 9.3% butanol, 90.7% water, and the butanol-rich phase would be 64.5% butanol, 35.5% water. Now, this is an interesting nuance, but notice that nowhere did it say what the composition of the initial mixture was. So am I adding water and butanol 50-50? Am I adding 75% water to 25% butanol? What am I doing here? And the answer to that is that it doesn't depend on composition, and that's an interesting caveat, but it does figure into the parameters of A12 and A21. Actually, what's really going on here is that the composition is not a function of the initial composition, but with the material balance, you can figure out what the relative amounts of the phases will be. So for instance, if I had a 50-50 butanol water mixture to begin with, and I had phase separation occurring, I would have roughly equal amounts of the alpha and the beta phases. But let's say I added 10 parts water to 1 part butanol. I would still have 2 phases that are separating, but I would have 10 times as much of the water-rich phase as of the butanol-rich phase. And obviously that's just a back-in-the-envelope type calculation. You still have to do a material balance in order to figure out what the exact distribution of the 2 phases are. Anyway, that wraps up this practice problem, wraps up another week of phase equilibria. You should be getting excited. We have officially 2 weeks left of this semester, and see you next week.